Hello students, good morning. In the last video, we looked at the defects and the concluding part of that video spoke about Frankel defect. So we did a Frankel defect. Frankel defect basically it spoke about uh, the defect which arises when the ion goes missing from the regular lattice and occupies interstitial position. Correct? That's what we saw in it. Right, so as the diagram itself says, there is vacancy of cation and then it goes and occupies the interstitial position in the crystal lattice. Okay, let's continue. So the conditions for the formation of Frankel defect, so this defect occurs in ionic compounds, as we know, with large difference between sizes of cation and anion. Remember, in Schottky defect we looked at uh, there would be very small difference between sizes of cation and anion, but in this case there is large difference between sizes of cation and anion. So the ions of ionic compounds must be having low coordination number. Okay, so which means there would be very low coordination number. Since there would be low coordination number, the attachment would be very less. Okay, now what are the consequences of Frankel defect? As no ions are missing, remember in Schottky defect it just goes missing, right? So let me just take you to Schottky. See, it goes missing. It doesn't occupy the interstitial position. It goes away completely, right? And because of that, what happens is the mass also should be reducing, correct? But in the case of Frankel defect, what happens is as no ions are missing from the crystal lattice as a whole, the density of solid and its chemical properties remain unchanged. Okay, the crystal as a whole remains electrically neutral. Why? Because the positive and the negative charges they are equal. Okay, that's why the electrical neutrality remains intact. So in which compounds this defect is generally found? It's found in zinc sulfide, silver chloride, silver bromide, silver iodide, okay, calcium fluoride. So these are the ionic compounds in which you'll find Frankel defect. So quickly, if we want to find out the difference between Schottky defect and Frankel defect, in Schottky defect, you'll find vacancy, okay, but in Frankel defect, that vacancy that is created by a cation or an anion, it goes and occupies some other position which we call it as interstitial position within that crystal lattice. Okay, let's continue. So we are done with stoichiometric point defect, my dear students. Okay, let's go to letter B, that is impurity point defect, or it's also called as impurity defect. So as I mentioned earlier, the word itself says impurity defect. That means there should be some impurities or some foreign item, some external impurity that would be added into it. Okay, so impurity defect arises when foreign atoms, that is atoms different from the host atoms, are present in the crystal lattice. Now how many types of impurity defects are there? There are two kinds of impurity defects. One is substitutional impurity defect. Okay, so the word itself is quite understandable for all of us. Substitution, that means you take my place, I'll take your place, that way. So that's substitution, right? In football match, okay, there are 11 players, so when one person is added, okay, it becomes 12. So but then there is no possibility of one person being added, there is only a possibility of substitution. So in the end, in the football pitch, one team can have only 11, okay, because the player is substituted. So in the same way, in this defect, what happens is the foreign atoms are found at the lattice sites in place of host atoms. Okay, now for example, suppose if copper is my host atom, okay, it is replaced by zinc, as it is shown by this black color. Okay, so zinc atoms, it substitutes copper atoms, as you can see in this diagram. Okay, so the regular atoms are displaced from the lattice sites by impurity atoms. Okay, generally something like this happens in preparing alloys. So brass is an alloy of copper and zinc, isn't it? So in brass, what happens is host copper atoms uh, is rather replaced by zinc atoms, and the zinc atoms occupy regular sites of copper atoms. Okay, now vacancy through aliovalent impurity. Now there is also vacancy that is created because of some impurity. Remember, we are doing impurity defects. Now what is this aliovalent? Vacancies are created by the addition of impurities of aliovalent ions. Now what is aliovalent? Ions with oxidation state different from that of host ions. That means the oxidation state of that impurity that is added is different from that of host. Host means a crystal lattice which is originally made up of. Okay, so in this case, originally this crystal is supposed to be of copper. So copper should have been the entire occupant over here, but zinc acts as an impurity over here. Okay, similarly here, what happens is sodium chloride is my host, that is Na plus Cl minus, Na plus Cl minus, but strontium chloride is added as that compound, okay, that aliovalent ion, because strontium has got a different oxidation state. Strontium has got OS plus 2, that's oxidation state is plus 2, wherein sodium has got plus 1. Okay, so suppose a small amount of strontium chloride, as you can see over here where my cursor is, Sr2 plus. Now Sr2 plus, 2 plus is the oxidation state and Na plus is plus 1. That's why the oxidation state is different. Suppose that a small amount of strontium chloride impurity is added to sodium chloride during its crystallization. The added Sr2 plus ion, remember SrCl2, strontium chloride, its oxidation state is Sr2 plus. The added Sr2 plus ions occupy some of the regular sites of Na plus host ions. Okay, now in order to maintain electrical neutrality, every Sr2 plus ion removes two Na plus ions. Why two Na plus ions? Because this is Sr2 plus, and that's why to just nullify or make it electrically neutral, two Na plus needs to be added, or rather removed. So if I'm adding one Sr2 plus, that means I need to remove two Na. So one is removed from here where my cursor is, and one which is removed, Sr2 plus has gone and occupied its place. So two Na plus is removed, one from here and one from here, and one Sr2 plus is added. Okay, the other site of Na plus ion remains vacant, as you can see in the figure. So that is vacancy through aliovalent impurity. Does it come under impurity point defect? Definitely yes. Okay, next is interstitial impurity defect. Okay, so the first one was substitutional impurity defect in impurity point defect, and second is interstitial impurity defect. Now what is the difference between the two? In this case, what happened was there's an external substance that occupied or replaced or substituted the host atom. Correct? Zinc replaced copper. Straight away, 1, 2, 3, 4 copper atoms were taken out and zinc took its place. Whereas in this case, that is interstitial impurity defect, as the word interstitial, the moment you see, my dear students, the word interstitial means it's some space in between the crystal lattice, like how you can see this carbon. Okay, so in this defect, the impurity atoms occupy interstitial spaces of lattice structure. Now, for example, in steel, okay, now steel is also an alloy, isn't it? It's made up of iron and carbon. So iron atoms occupy normal lattice sites. So the entire orange atom that you see over here, they're iron. They are not moved at all. But what carbon does is carbon goes and occupies those interstitial spaces. Okay, is that an impurity defect? Definitely yes, because the host is actually iron, but carbon has come like one foreign agent over here and has occupied the space uh, in the crystal lattice. Okay, and the last one is non-stoichiometric defect. Now in non-stoichiometric defect, my dear students, as I mentioned, there is a change in chemical formula. Okay, so let's take a look at this in detail. It arises when the ratio of number of atoms of one kind to that of other kind, or the ratio of number of cations to anions becomes different from that indicated by its chemical formula. Okay, so basically what happens is the stoichiometry gets changed. Because the stoichiometry gets changed, that's why we're calling it as non-stoichiometric defect. Okay, but even though stoichiometry is getting changed, it does not cause any change in crystal structure. Now there are two types of non-stoichiometric defects. One is metal deficiency, okay, and the other one is metal excess. Now again, these words are very simple for us to understand. The meaning of metal deficiency means there would be removal of a metal ion, and metal excess would be, there would be an addition of metal ion. Now this defect is possible only in compounds of metals that show variable oxidation state. I repeat, this defect is possible only in compounds of metals that show variable oxidation states. Now, for example, this is nickel oxide crystal lattice. So there is Ni2 plus O2 minus, Ni2 plus O2 minus, Ni2 plus O2 minus, and so on. But there is another Ni with a variable oxidation state, because Ni is an element in the periodic table that shows variable oxidation state. So it also exists in Ni2 plus oxidation state. It exists in Ni3 plus oxidation state also. So this defect is possible in those compounds of metals that show variable oxidation states. So there is Ni3 plus that you can see in the pink over here. Okay, so Ni3 plus and Ni3 plus. So 1, 2 and 3 Ni2 plus are removed, and 2 Ni3 plus. Okay, 2 ions of Ni3 plus, they have occupied these two, and third one is kept vacant. Okay, so there is a vacancy that is created over here. So that's why there is a metal deficiency defect caused because of a metal that has variable oxidation state. So because there is vacancy here, that's why it is metal deficiency defect. Now what is this metal excess defect? Now again, in metal excess defect there are two types. Students, if you noticed, when we started defects, there are so many types within types. Okay, so you need to be very careful. It's very simple to understand. It's just that you need to be a little bit alert and careful while studying these defects. Now what is metal excess defect? It's explained in two types. So for example, ZNO, that is zinc oxide. Okay, now zinc oxide presents two ways of metal excess defect. In the first case, ZNO lattice. So the entire lattice is zinc oxide lattice. So one neutral Zn atom is present in the interstitial space as shown in figure. So you can clearly see ZNO, ZNO, ZNO. It's nicely arranged. So it's a perfect lattice here. But an excess neutral Zn atom is added in the interstitial space. Okay, that means a neutral atom or an extra positive ion occupies interstitial position. Such kind of defect is called as metal excess defect. Or by anion vacancies. Now there is plus minus, cation anion everywhere, but there is an anion vacancy that is created, okay, which has also led to a metal excess defect. So something like this you'll find. So an electron is added over here. Okay, so here in this case is a neutral atom or an extra positive ion. Here an anion vacancy. Okay, so something like this you'll find in metal excess defect. So quickly, my dear students, we'll just recap this and end this video before we go to the next and the final video of this chapter. Okay, so we did the conditions for the formation of Frenkel defect and the consequences of Frenkel defect. Impurity defect. In impurity defect there is substitutional impurity defect, and then there is interstitial impurity defect. Correct? Then in non-stoichiometric defect there is metal deficiency defect. Then there is metal excess defect, right? So these are the things that we've seen in this video. So basically this entire video has gone in studying about defects. Okay, quite an interesting concept for all of us to study. In the next video, my dear students, we'll study about some properties of solids, which hopefully would be the last video to do with the theory of this chapter.